Okay, so soluble covalent solutions are going to basically exist by individual dispersion particles throughout the solution. So in other words, you're going to be paying attention to the polarity, whether or not something is going to dissolve nicely, right? Or it's going to be dependent on dispersion forces, whether it dissolves, right? So things that are non-polar, they're going to be able to dissolve in non-polar solutions, where things that are polar are going to be able to dissolve in polar solutions, or ionic are going to be able to dissolve in polar solutions. No. So like for instance, if we have oil and water, right? Oil is non-polar, water is polar. And so if we mix that together, you're not going to get them to dissolve in each other, right? Okay, so methanol basically at room temperature is like, okay, so here we have methanol liquid, right? But when we add water to methanol, we put the aqueous sign. Okay, now methanol is polar, right? It has that hydrogen, it's able to form that hydrogen bond, right? And so since methanol is polar, it's going to be soluble in water. Okay. And so you're not going to be able to see, like, you don't get that clumping like you would get in the case of oil. Okay. And normally I'd have a nice little picture of water, methanol, and it coming together, but let's pretend that we have that picture instead of a nice blue screen. Don't worry, I'm working on it. Next week I'll have my slides. So soluble ionic solutions basically will go dissociation. Like for instance, sodium chloride. So when we put salt in water, what happens? It dissolves, right? It basically will disperse throughout the entire thing, and you can tell, and basically our ions are separate. We have our plus. Let me draw this out. This is going to drive me crazy. Oops, sorry. Where's my mouse? So if we have sodium, and then we have water, so we know that sodium is going to react or interact with the oxygen. And the chlorine is going to interact with the hydrogen, right? And so that's what's going to keep it in solution. So this guy's going to form a hydrogen bond to keep the chlorine ion in solution. And then the oxygen is going to interact by what force? With the sodium by what force? The oxygen is going to interact with the sodium by what force? So if the hydrogen is interacting with the chlorine by hydrogen bonding, the oxygen is interacting with the sodium by what force? Does oxygen have a hydrogen on it? Well, it has one, but what was that? It is intermolecular forces, but which force? That's what I'm asking you. Dipole, right? So in this case, this would be dipole ion, right? Okay. Yeah, because one forms a dipole and one is an ion. Okay. Ionic dipole, yes, or dipole ion, yeah. Okay, so if we have potassium dichromate, it it's basically solid at room temperature, right? So when we add it to water, we know that it dissociated into its ions. And depending on how soluble it is, it's going to dissociate almost instantaneously. The more soluble it is, the more instant it's going to dissociate. Okay, so if a solution formation requires a high enough energy threshold, the solution will not form. Okay, so some things will happen instantaneously, spontaneously, right? And some things require us to put energy in it to get over a threshold, right? So it's basically saying that in some cases, some ionic compounds, they won't separate, right? They won't separate from themselves unless you put energy into it. Okay, so like for instance, barium hydroxide is an example. So barium hydroxide, it will separate into ionic components, but you have to put a little bit of heat into it to get it to happen. Okay, and so that's an example. Now, if the energy is too high, then we won't be able to do it. So like for instance, if we look at ceramics, right? Now we could actually cook water in ceramic bowls and things like that, right? Does that ceramic bowl separate? Even though we know that those are composed of two ionic components that have come together. Okay, so you guys are good on that? Like, so think about barium hydroxide. What are the components of barium hydroxide? Barium is a what? You're going to form an ion, yeah, that's true. But barium is a metal, right? And you have metal and OH, right? So, and that's going to form an ionic compound, right? So it's not covalently bonded, it's ionically bonded, right? Yeah. And so even though it's ionically bonded, we put in water, we would assume that it's going to separate, right? Barium is group 2 metals, right? There's certain group 2 metals that will separate, and there's other ones that don't. Most of them do, okay? But barium doesn't. It takes a little energy initially. So if we put barium hydroxide in water, it doesn't break down initially. It actually will stay together for a little bit, and it takes a little bit of heat to get it to break down, okay? Aluminum hydroxide, it won't break down. It'll stay together, right? It's partially based upon its solubility. It's also based upon the energy that's going to be required. It takes a lot of energy to be put into that system to make it happen, right? It will react with things, but it won't break down on its own. Like if we add it to water, it won't dissociate into aluminum ion and hydroxide ion. That's right. Not that's something entirely different because you're taking in consideration the ionic character of the compound that we're talking about, right? So, and how comfortable they are with being together. If it's, you know, it's just known that certain ions, the way that they behave, because of that metal and how many electrons and stuff like that, it's going to be try to stick to things better than other things does. Yep. Yeah, so typically they're going to be givens. There's tables and tables and tables. The only way that you typically know it is either you remember the tables, which we're going to be talking about. And part of it, do you guys remember when we talked about the solubility table? And if you guys look on your periodic table, of course, I forget mine. Yep. And it tells you what's going to be soluble, what's not going to be soluble. You remember that? Not the activity series, not that one. That is important, but yeah, there's one, not that one. There's one more. Keep going. Nope. It'll be one that has like test tubes of things on it. Do I not show it? Did I not say that one? Let me see. Maybe. I know you guys are right. No, it's not that one. Yeah. I didn't. You know what I'm talking about. One of the actual big things. Yeah. Yeah, I have another package. Remind me later that I'll do it after that. Let me see that one again. The one that you have the what happened. No, I'll print it out for you. But anyway, the point is that certain compounds are going to take energy to sit there and dissolve, right? Okay. So, however, many solutions are going to be spontaneous, right? So then they basically have a low energy, and so they're going to dissolve spontaneously. And then, and this process, right? This process is going to be dictated by entropy. Okay, not enthalpy, entropy. Okay, entropy is kind of like order. It has to deal with order. Okay, so entropy is basically described as the disorder of a system. The low disorder, low disorder is highly organized, while high entropy is highly is disordered system or highly random. Okay, so the higher the entropy value, the more random it's going to be. The lower the value, the more organized it's going to be. Yes. So that kind of plays a part in that, you know, whether something is, we're talking about different types of solids where it's amorphous or, you know, or crystalline, right? So systems can go from a low entropy to a high entropy. And this can drive the formation of a solution. Okay, so barium hydroxide is a low soluble in water. So basically it's almost insoluble in water. But if we add a little bit of heat, we get the ions to form. Okay, barium hydroxide. It's so funny, I didn't even think about that. I had this in the notes. So now, if the intermolecular forces versus intramolecular forces, right? IMFs, right? So those substances are similar to the solvent. You're basically going to negate the change of energy, right? That's going to be required for that solvent solution to form. So in other words, that's kind of like likes like, right? So we were talking about water and methanol. Methanol will dissolve in water because you have hydrogen bonds. They have like things. And if we're talking about lard and oil, right? Oil will dissolve in lard because, or lard will dissolve in oil, depending on which one, because they both have that non-polar, those dispersionary forces, right? Okay. Now, sodium hydroxide is highly soluble in water, and this is going to be spontaneous, right? So that means that, boom, instant, it's going to happen, right? But the thing is that as a result of that, we're also going to get heat formed, right? And that's because of the increase of entropy due to the dissociation of the atom, okay? So if entropy is increasing, that means disorder is increasing, right? So initially it's ordered, and then we get to disorder by breaking those bonds or by dissociating the ions, right? Ammonium nitrate is used for coal packs. So due to its spontaneous formation, it'll actually decrease the temperature, right? So if we put ammonium nitrate in water, what happens? It will get colder. Okay, so this is an example that small amounts of energy are going to be required for solutions to form. So in this case, it's taking energy from the system, right, to sit there and allow for this reaction to happen. Okay. That's right. So if it's going to be lower in entropy, if you're going from like a higher state to a lower state in terms of entropy, right, then that is going to be an endothermic reaction. And then exothermic is when you're going from a low and you're going to a high state. So you're going from an ordered state to a chaotic state, right? So, and then that's going to result in heat being released, right? So then in that case, you're going to have an increase in entropy, right? So, because that just basically from order to disorder, that's increase of entropy, okay? And then from the other case, we're going from a sort of a disorder state because it started off in a disorder state and we're going to an ordered state. So then that is going to be an example of us lowering the entropy. So we're getting an endothermic reaction. So it requires energy to be put in that system to get it organized. Are you guys with me so far? Again, I apologize. These are going to be rough slides. Okay, so you're talking in the very first one. So it says the solubility increases, allowing the water to solvate the ion. That basically means that it causes the water is going to dissociate the ion, or the water is going to be allowed to help the ion form, right? So it's being used as a verb, right? So it's just dissolving, right? It's a nice way, another way of saying dissolving. It's, repeat that, please. Okay. That's right. That's right. Okay. Okay. Well, just got to notice that I've been exposed to COVID. Okay. So it's good to know. That'll be my third test in this, well, last 3 weeks. So every week I've been tested. So yeah. Yeah, I had one 2 weeks ago, I had one last week, and I had one this week because I've been exposed. I've been in meetings and things with either students or with who are We've been COVID positive. I have a couple students that are really sick right now. So yeah. Yeah. And I'm like, I can't afford to be sick. So yeah. There is a strong possibility at the rate that we're going, which I hate. Oh my God. So I need to start getting ready for this. What was that? Oh my God. Yeah. Well, see, they're already ready. Marisol and Abel, you know, they're like, yeah, we're already good. What are you complaining about? Okay, so electrolytes. Okay, so this again deals with that concept of dissociation in a sense. Okay, so the property of a solution. So if it's able to conduct electricity, right? That's going to be mainly due to the fact that there's ions dissolved in that solution, right? So let me grab something real quick so I can show you guys. You guys, can you hold on for a minute, Abel and Marisol? You're not jumping ship. You're saying this blue screen is killing me, right? Battery, you guys see at home? And I have a battery, and then a little LED, right? Okay, we get light, right? Can you guys see light? Let there be light.
Yep.
Okay. Okay. So if we have an ionic solution, I can put both of these electrodes in there and not connect it, and I should get light if it's ionic. This is sodium bicarbonate. Ionic. Okay. Now, if I have water, I'll go. Ionic. Jug of water here. This is the still water. What's that? Yes, thank you. You know, we'll be ions off of it. We won't make me into a liar. Okay, so I'm gonna put distilled water. Okay. Any light? Do you guys see any light? No light, right? Okay, so we know that ionic solutions, when they're completely dissolved, we're able to get conductivity of electricity. When ions are completely dissolved, right? When it's partially dissolved, we'll get a little bit of light, but just a little bit of light. So like weak acids will cause it to light up a little bit, but not much. You know, they have a lot of ions in them. Pardon me? Through potatoes? Ionic dissociation. Well, no, there's a couple of ways that you can get the electrons moving, right? And so the key is just the generation of electrons moving, right? Well, we know that ions are electrons, you know, they're charged particles, right? And so we're just moving those charged particles in that solution. Okay. Oops. Get carried away. Okay. So ions could either, so they could either dissociate, or they could end up staying together, or they could result in another chemical reaction, right? So those ions, okay? So that process of them dissociating is more of a physical process, more so than a chemical, but you could get it either way. You know what I'm saying? So a strong electrolyte is going to be 100% dissolving of ionic solution. A weak electrolyte is going to be, you know, less than 100%, much less than 100%, right? Yeah, I'm going to have to fix these slides. They're suck. Well, let's think about, no, they're forming ionic type of reactions, because in the case of water, water is partial positive and partial negative. They form dipole, but there's not enough transfer of electric current to allow it to conduct electricity, okay? And that's gonna be really important, right? Okay, solutions with no significant conductivity, they're non-electrolytes, okay? So electrolytes are going to basically be defined as soluble ionic solutions, okay? Questions, concerns. So most common electrolytes involve ionic dipole solutions, right? So that's like my example of the sodium and the chlorine breaking up here and the water interacting with it, okay? So for solubility determination tables, okay, so in other words, let me put this simply, there are tons and tons of tables that deal with solubility. You guys have one of those, the grid in the back, which you were talking about, but that's not the one that I was looking for, but that's an example of a solubility table, right? So things that dissolve and things that don't dissolve, okay? So in your packet, did I throw my packet away? I thought I brought one in. Okay. I have just my box. Yeah, I'm a hot mess today. It's okay. Oh yeah, sure. You don't like my letters there? Okay. So when we talk about solubility of a solution can be described quantitatively using the solubility tables like we talked about, those tables that you guys have. I'm sorry, qualitatively. And they can also be defined quantitatively by using solubility data. So in other words, we have to do experiments to determine how soluble things are. And again, there are tons and tons of tables that people have done over time. If you guys go in the chemistry Bible, which is in the other room, I call it the chemistry Bible, but if you go there, they have tons and tons of solubility tables in there. You guys don't know what I'm talking about? Not Appendix G, yes. Although in Appendix G, I believe that there is some solubility table, but that's not the one I'm talking about. I feel like this is a shortcut today. So this is the chemistry Bible. It's actually called the Handbook of Chemistry and Physics. And as you can see, it's about a $500 book. And now it's probably more than that. Maybe $1,000. But what was that? Oh yeah. And when we talk about, it has every possible table that you could possibly need for tons and tons of chemicals that have been studied. No, not really. Not really. Is it? It's because there's only a select few people that would actually buy it, right? Chemists, right? And so they can only sell it to a few people, so they sell it for so much money. Now you can actually download the database. You can get the database, do searches on it, but you pay a subscription to it. So, you know, and during the time period, there wasn't the internet, you know, so we were very limited. We can't search Wikipedia to sit there and get the or P table and get the solubility information on. Okay, so it was very, very limited during the time period. Okay, so in other words, you can find this table, you can figure out if it's going to be soluble in water. Okay, and usually solubility is going to be defined at room temperature. So it's going to be that solvent at room temperature. So specific solvent at a specific temperature. Okay. So qualitatively describing solutions include whether it's unsaturated, right? Unsaturated basically means that it's not soluble, right? Saturated basically means that okay, so what do I mean by that? Because you guys have heard of saturated fats and unsaturated fats. Okay, saturated fats basically means that you put in all of the hydrogen so that there are no double bonds. So in other words, you're taking up all of the space that you could possibly take up without precipitating, right? So that would be saturated. Unsaturated means that if it's unsaturated, there's a lot of space that is available, right? Okay, then we get into the point of supersaturated. So basically supersaturated means that you set up a condition that you put in over the amount. So let's say there's students and there's 50 seats in the classroom. And then I decide I'm going to let in 60 students, right? That means 10 of them don't have seats. I can't do math today either. Oh. So 10 of them don't have seats. So that would be an example of supersaturated, right? Where saturated means that we have 50 seats, all 50 seats are taken up. Unsaturated means that we have 50 seats and only 30 seats are taken up. Does that make sense? Okay, now gas solubility is going to be dependent on pressure of the gas above the solution that's being described. Okay, and this is going to be described by my law, Henry's law. Okay, and I just didn't put this up in here. Henry's law existed well before I was. It was my great-great-great-grandfather who discovered this. Even if it wasn't, I'm going to say that just for the hell of it. Okay, so I'm going to give you guys a nice little, cute little solubility table. We talked about this in last semester in like the first chapter, and my table is a little bit better. Yeah, yes, it was, yeah. So ammonium compounds are going to always be soluble. So if you guys take a look on your packet, the table, and you look at ammonium, if you look at ammonium, they're going to always have green, if I remember correctly, right? Okay. Acetates are soluble except when they're with aluminum and silver. So if you take a look at acetate, you guys see acetate on there? Yep. So all the ones, yep. So chlorates and chlorates are going to always be soluble. Okay. Nitrates are always going to be soluble. Nitrites, they're all going to be soluble except for silver. Chlorides, bromides, iodides are going to be soluble except for with silver, with mercury, and with lead. Fluorides are going to be all soluble except when they're with magnesium, calcium, strontium, barium, and lead. And we know that hydrogen fluoride doesn't dissociate. Let's see. Most sulfates are going to be soluble except for group 2 metals and silver, mercury, and lead. I'm sorry, mercury 2, not mercury 1, mercury 2. And sulfites are going to be insoluble except for ammonia, group 1 metals, and magnesium. Carbonates are going to be insoluble except for group 1 metals and ammonium. Phosphates, same thing, insoluble except for group 1 metals and ammonia. Sulfides are going to be insoluble except for group 1 metals and ammonia. Most hydroxides are insoluble except for group 1 metals, ammonia, and barium if we add a little bit of heat, barium hydroxide. Most oxides are going to be insoluble, and all acids are considered soluble because they do not dissociate enough, because they dissociate enough to have the ions. Now, strong acids are going to be very soluble. Weak acids are going to still be soluble, but they're going to be a little less soluble. Does that make sense? So, let's see. Most gases are considered to be insoluble, such as hydrogen sulfide, methane, ammonia, and oxygen. Okay, so this is Henry's law. Okay, Henry's law basically states that the partial pressure of a gas above a solution is proportional to the concentration as a dissociated solute, assuming the gas doesn't react with the solvent. Okay, so if there's no reaction and you put a gas in, okay, so it's going to be dependent on that partial pressure of that gas. Okay, so Cg represents the concentration of the solute. K is just going to be a constant. And then Pg is going to be that partial pressure. Okay, so using this equation to basically calculate the solubility of nitrogen gas in water. When the partial pressure of nitrogen above water is 1.10 atm at 0 degrees Celsius, the solubility of nitrogen in water is 8.21 times 10 to the minus 4th molar at 0 degrees Celsius, with a partial vapor pressure of 0.790. Okay. So in this case, you have the concentration, Cg, equals K Pg. So what they're looking for is so they give us the problem. Let's see. Sorry. Let's use this. Hold on. Give me 1 second to get my pen together here. So we have okay, so the solubility of nitrogen in water is 8.21 times 10 to the minus 4th molarity at 0 degrees Celsius with the pressure. So in other words, first thing that we need to do is find that constant. So we're going to use this part here to find our constant. So that's going to give us our concentration or our solubility, right? So you're going to say 8.21 times 10 to the minus fourth molar is going to equal K PG, where PG is going to be equal to, what's that? .79 ATM. So we need to solve for K. So then we get K equals 0.790 ATM. Oops, sorry. Again, brain's not working today. K equals 8.21 times 10 to the minus fourth molar divided by 0. Can you see that red on blue? It's a little bit difficult. Okay. So I'll change the color for you. So we'll find a color that works. Okay, let's see. So funny. Nobody calls me when I don't have anything to do, but soon as I'm in class, everybody wants to talk to me. Although it's pretty true that I don't have too much free time anyway, but so we get 0.00103. Okay, so now that we have K, we can use K to sit there and calculate our solubility for 1.10 ATM. So then we just use our partial pressure, this equation here. And so to solve for our CG, so our CG is going to equal 0.0013, 103. Is that better, the yellow? Times 1.10 ATM. And I'm running out of room. Capital M is for molarity. Yeah. So CG is going to equal 0. Let's see. Let's just do it in scientific notation. That's right. 1.13. Actually, I get 1.14 because if I've done it right, it should be 1.137 would be the next number, and you round up. So 1.14 times 10 to the negative 3 molar. You guys get that? You had that look.
Like
1.04. Yeah, you're right. It's 1.04 because I rounded when I shouldn't have rounded there. So that should have been more. I mean, I didn't round. So 1.04. You're right. But then that times 1.14. Oops, sorry. It is one of those days. 1.10. Yeah, I still get 1.14 times 10 to the. Yeah. Okay. Okay. Questions, concerns, Cash, Kool-Aid. Okay. Again, I'm apologizing for these slides. There are a lot of words and not enough pictures. Okay, so a colligated properties. So colligated properties is a change in physical properties of a solution due to the amount of dissociated solute. So in other words, if we look at like melting point or freezing point or boiling point. So like you guys make pasta, right? Have you guys ever made pasta before? Right? It didn't come out good. Okay, so but when you boil the water, you add salt, right? What was that? Uh-huh. So you add salt to it. Why do you add salt to it? So it can cook faster. Okay, but why would it cook faster? Are you sure? Thermal conductivity. Mm-hmm.
In water.
Mm-hmm.
It's like kind of like it passes through easier. So what does that also calculate to the thermal?
Okay, so what does it do? What is happening to that water? So water normally boils at 100 degrees Celsius. If we add salt to it, what's going to happen? Its boiling point is going to go up. So in other words, it's going to be hotter. So the water is going to be hotter. So it's going to cook the pasta faster and you don't get soggy pasta. So adding solute is going to affect our boiling points, right? So if we add sugar to water, right? Have you guys ever made simple syrup? Simple syrup? Okay, what was that? Is that for drinks? Yeah, you can use it for drinks, but you can also use it to keep cakes moist. But in the old days, my grandma used to make it. So instead of having you guys like maple syrup and stuff like that for pancakes and stuff like that, they would actually make simple syrup, which is just sugar and water, right? And so you sit there, you think about that, it does exactly the same thing. It causes the temperature of the water to be hotter. Okay, so our boiling point is going to be able to elevate as a result of that. And then our freezing points are going to depress, right? And so that's what happens in the case of adding salt to ice, right? So when you put salt on the ground, so then, in other words, it has to be colder for it to freeze. So like for water to freeze, if you have salt in it, it has to be colder than 0 degrees Celsius. Does that make sense? Yeah. Okay. Okay, so measurements of correlated properties sometimes include the use of mole fractions and molality. So this is that term molality. We've talked about molality before when we talked about solutions. And so here we get a chance of introducing it again, molality. They're different. Molality and molarity are two different things. Don't mistake them. Yeah, I thought, oh, somebody made a typo when I first saw it. And I'm like, but molality, I can't even say it. See what you did to me? Salama. Okay, molality causes its moles of solute over kilograms of solvent. Molality. It does have molality. Molality. Okay, where molarity is moles of solvent over liters of solution. Not quite flipped. It's the same. It's moles of moles of solute. So it has solute. So molarity, let me use a different color. Sorry. Molarity, which is capital M, equals moles solute over liters. Yes, but the only thing that this is liters of solution. So it's both the solute and the solvent and the solute. Yeah. Okay, where this deals with just the solvent. Okay, so it's like a ratio. You're telling me how much solute in moles that we have over kilograms of solvent. Okay, so mole fraction is defined as the moles of the specific divided by the moles of the total. So it would be, if we're talking about a solution of water or something like that, it would be the moles of, let's say, salt and water. The moles of salt divided by the moles of salt plus water. And that would be our mole fraction. Okay? Now, this here is actually incorrect. So, what they're saying is it really should be X. So XA, XB is going to equal 1. So the mole fraction of A plus the mole fraction of B is going to equal should equal 1. Right? And that makes sense. Right? And that's what the sum, this should be XA, XB. Okay? So it shouldn't be in A and B. Does that make sense to you guys? You want me to show you the math? Because NA over Na plus Nb plus Nb over Na plus Nb is going to equal 1, right? That's right, because this, they have the same common denominator. So then you're just going to end up with Na plus Nb over Na plus Nb, right? Same common denominator, so these guys can just be added together. Does that make sense? And so this guy really should be X here. So this is the mole fraction of A. Mole fraction of A is defined as this. So the mole fraction of B must be defined as Nb over Na plus Nb. Sorry, I keep going back to that damn red. Let me fix my red color. Sorry. Good yellow. Okay. And so when we do fractions, we know that these guys are the same common denominator, so you can just add the top together. Right? That's kind of like if I say 1/2 plus 3/2. Right? We know 1/2 plus 3/2 is going to equal 2. Okay. Okay. Okay, so vapor pressure of a solution is going to be defined as, it's going to be using Raoult's law. Raoult's law basically says P solution is going to equal the mole fraction of the solvent times the partial pressure of the solvent, of the pure solvent. Okay. Piece of cake, not too hard to remember, right? So P solution is going to equal P, or the mole fraction of the solvent times the pure vapor pressure of the solvent. Okay, so we're going to work it out. Let's see how it works. So it says here, the vapor pressure of a solution containing 53.6 grams of glycerin dissolved in 137.7 grams of ethanol is 113 torrs, 113 torrs at 40 degrees Celsius. Calculate the vapor pressure of pure ethanol at 40 degrees Celsius. Okay. So what do we need to do? First thing first. Find the mole fraction. Okay, so how do we find the mole fraction? First, we need to find what? Do we have to find molality? How do we find the mole fraction? How do we find the number of moles? Okay, so we're given 53.6 grams of C3H8O3. Okay, so how can I change that to moles? What do I need to change that to moles? The molar mass. So what is the molar mass? So we'll put it up here in this corner. So we have 3 carbons. So that's 3 times 12. If I remember correctly, that equals 36. Oh my God. Can you find 20 of them? Okay, that's good. 5, so now we need 15 more. Oh, wow. Oh, wow. Okay, so let's put those in a box. I think I have a box in our chem room. Put them in there so if we can find. Okay, sounds good. Thank you. The best. I have the best TAs. 8 times 1, 92.094. 92.094. So let's say 92.1. Okay, so that's grams per mole. Okay, so then that gives us okay. So we need to do the same thing for the ethanol. C2H5OH. $46. So we get 2.0, oops, sorry, 90. Brain is not working today, 91. Sorry, 2.91. Actually, 4 sig figs in this case, so 0.7. Brain is not working today at all. And this is ethanol. So our mole fraction, ethanol is our solvent. So we're looking for the mole fraction of the ethanol. So I'm just going to use ETOH for abbreviation for ethanol. So that's going to equal 2.907 divided by 0.582 plus 2.907. Yep. It's 24 plus 16. So 24 plus 16 is 40 plus 8 I mean, not 8. Oh, wait a minute. Did I say 8? Oh, 6. 6. It looks like a 3. I'm sorry, my bad. It's a 2. My 2 looks like a 3 right there. Yeah. Okay, so that's. Okay, so I get, for my mole fraction, I get 0.833 2. Okay. What was that? Right here? Or down here? Sorry. Oh yeah, it doesn't show. Oh, my bad. Okay, so then this gives us our mole fraction, right? And so we're trying to calculate the partial pressure, of the vapor pressure of the pure ethanol. So we're using this equation. Change my color. Oh, no, let's not be blue on blue. That's a crime. Try purple. So we're doing, oh yeah, that does not show at all. P equals X solvent, P solvent. Okay, so we're going to be solving for P solvent, right? We're given the partial pressure, which is 113 torr. So we have, yeah, the thing about pressure units, it's multiplied, so you can keep it the same unit. You don't have to worry about doing the conversion. Okay, so we go partial pressure divided by our value, which is 0.8332, and that's going to equal P solvent. Times 3. So 3 6. So it should be 136 torr. I hate this. I keep running out of room. Okay. Questions? So it's just a lot of plug and chug, right? And just remembering, okay, moles. Okay, how do I calculate mole fraction? It's going to be torr, it could be ATMs, it could be, you know, long as you, whatever unit that you have, you can end up with, right? So long with pressure. That's the big beauty of pressure. Okay. So you guys aren't going to mind me completing these slides so that we can try to stay on top track. You guys at home, especially since your lab is a dry lab that deals with all of these equations. Did you guys see that? Your new lab? Yeah, but we have to finish. We have to finish our other lab too, right? Yeah, we'll finish it. And I brought some ice, so yeah, it's been a rough day. Okay, so correlated properties. So when we talk about our boiling points, our freezing points, so the change in boiling points and the change in freezing points, right? So those are all going to be dependent on the molality, right? Not molarity, molality, okay? So here, KB represents the molality boiling point elevation constant. That delta T represents that change in temperature, okay? So if we're given one of the temperature points, we'll be able to calculate the change based upon the change in temperature, okay? And delta T is going to equal for boiling point. So the change in temperature and boiling point is going to be KB times the molality. And then for freezing point, it's going to be the same thing. Only thing, instead of using the constant for boiling point, you're going to use the constant for freezing point. Okay. So calculate the molecular weight of a compound, use an antifreeze for 0.24 grams of an unknown solute dissolved in 25 mils of water with a freezing point depression of 0.201 degrees Celsius. The Kf for water is 1.86 degrees Celsius over molality. Don't have that look. Just, oh, it looked like you had that fear going on. How are you guys doing over there, Abel and Marisol?
I'm doing fine.
Marisol?
I'm getting it.
You're getting it? Good, good. I know they're really dry slides. I'll work on that. They're going to be doing what? They're going to finish up their lab. Yeah. Okay, so where are we going to start from? So we have delta T, right? And delta T is, thank you. I am, again, the lowercase m is molality, yeah. Or molal, actually, to be specific. I am not writing 0.201 degrees C. Okay, and we know that Kf in this case is going to equal 1.86 degrees Celsius over molal. Okay. So we know the equation. Kf times molal equals delta T, right? So we just plug everything in. So we get 0.201 degrees Celsius equals Kf. Oops. Plug in what Kf is. 1.86 degrees Cm. And then we have the molal. So this is the units molal. This is the abbreviation for molal, okay? So in this case, we're solving for our molal, which is going to equal, so we're going to say M is going to equal 0.201 degrees C divided by 1.86 degrees C for molal. So then C's are going to cancel out, and we're going to be left with our units in molal, which is and we know that this is, what are the units? Would be moles per kilogram, yeah, over kg. And I keep running out of room. I keep running on the slides because I can't, it's hard to look behind me in. Okay. So we want to calculate the molarity. I'm sorry, calculate the molecular weight, sorry, not the molarity, the molecular weight of a compound used in antifreeze for 0.2. Okay, so then what are we going to do now? Because isn't it moles of solute over kilograms of water or solvent, right? So how can I change my water into so 1 gram, so the density of water is 1 gram per milliliter, right? So if we have 25 milliliters, then that means we have 25 grams of water, which we can convert to kilograms. So how do I convert 25 grams into kilograms? Divide by what? 1,000. Let's put H2O here. Okay, so then we end up with 0.025 kilograms of water. So then we take this value here. Do you guys mind if I erase this part over here? Can I erase this part? Okay. So we have more room to work. Okay. So we'll take our 0.25. Zero. 0.0250 kg, kilograms, and we multiply that by our molality, which is going to be 0.108 moles per 1 kg. Kgs are going to cancel out. And then we're left with moles of our okay, so that's going to equal 0.00270 moles. Gosh, I'm struggling here. Okay, so do you guys agree so far? Okay, so then we have our 0.02 moles, and I want to figure out the molecular weight. So I just take my grams and divide it by my number of moles. So I'll go 0.243 grams divided by 0.002, and now my computer is lagging again, 270 moles. And that's going to equal, come on. $89.9 grams per mole.
Pretty close, but I got like straight 90.
You got straight 90?
Yeah.
Okay.
But I mean, like, it's the same thing, but I don't know.
Yeah, well, I may have rounded at some point or did round at a point. So. Let me check. Yeah.
Straight number.
Yeah, actually, because I rounded here, but I didn't round on my calculator. I just used the number that I had. So. Okay, so 90. Piece of cake. Okay, so you guys notice that this so far, you're just basically using what you learned the last semester and you're applying it to specific situations. Now, the things that you want to remember are why those specific situations are occurring, right? Because those intermolecular forces, right? Okay. Keep on erasing. Okay, osmotic pressure. Okay, so when we're talking about like cells and everything like that, we often will talk about osmotic pressure. You guys heard of the membrane, right? The cell membrane. Yeah. You just learned this, okay. Okay, so the cell membrane is a semi-permeable membrane, meaning it lets certain things in and let other things out. So it's kind of like a bouncer, you know? A bouncer is like, oh, you're not old enough, you can't come in. Or, oh yeah, you're cute enough, you can come in, you know? So, so that's what we're kind of talking about here, okay? So some membranes will allow the solvent to come through, but not the solute, okay? And that's the same thing in terms of inside and outside of the cell, right? So you have the cell itself. There are things that are able to stay, that will stay inside the cell, will never leave the cell because that membrane won't let it out, okay? So even though a solvent may not be, a solute may not be able to pass through the semi-permeable membrane, there is going to end up being a concentration balance, right? Okay, because the solvent is able to go back and forth, right? And then because of that concentration balance, you're going to end up with pressure being applied across that membrane. Okay, and so that's really what happens, right? So ultimately, the membrane is going to allow the solvent to go back and forth, right? And if, let's say, I'm going to have you guys do an experiment when you guys go home. Do you guys have vinegar at home? Okay. When you guys get home, take an egg, just a regular egg. Don't break it open or anything like that. Stick it in vinegar for about 3 days. Okay. So after you've stuck it in vinegar for about 3 days, do you guys have syrup? Yeah. You have syrup? Okay. So it works best with syrup. So then take syrup and surround that egg that doesn't have any shell anymore, with syrup. Okay. Actually, we can do it in here. I'll bring everything in next week. And so what's going to happen is that ultimately we're going to affect that equilibrium, right? So we're putting a solution on the outside that's going to suck out all of the solvent on the inside, right? And so, because it's going to try to balance out, right? So what happens is that we try to maintain an equilibrium. So if it's more concentrated on the outside, then the solvent is going to go from the egg to the outside. If it's more concentrated on the inside, then the solvent is going to come from the outside and go on the inside, since the solvent is able to move back and forth. Yes, kind of like a free spirit, yes. Okay, so the cell itself has to maintain some type of equilibrium. It has to find a point where we're kind of balancing out what's on the inside to what's on the outside. Okay, now again, as a result of this, we're going to end up with pressure being applied on that membrane. And that, again, that's called the osmotic pressure, okay? Because we're looking at the flow of water coming in and out. So this here is the take home. Let me highlight. Can you guys see the highlight? Or not the highlight, you can see the highlight. You can see laser pointer. Can you see laser pointer? Good. Okay, so take home message. A cell with a greater solute concentration inside is going to be hypertonic. If it's equal concentration, then it's going to be isotonic. If you have a greater concentration on the inside, it's going to be hypotonic. Okay? Hypo meaning below, hyper meaning extra, more, right? Okay, osmotic pressure equation. Now, this is going to look very, very familiar. Pi equals MRT. Does it look familiar? PV equals MRT, where pi represents the osmotic pressure. M represents the molarity, which is moles over volume, right? R represents the ideal gas constant, and T representing temperature. Okay, PV equals nRT, right? Sorry. Okay, so a 10.0 gram sample of liver enzyme, which is called catalase, has a volume of 1.00 liters at 27 degrees Celsius. The osmotic pressure at 27 degrees Celsius is 0.74 torr. Calculate the molar mass of the catalase. Okay, so pi, oops. Using my laser pointer pretty well there. I want to use my pen. Okay, so we know that it's pi equals M R T. Okay, the first thing that we want to do is we have torrs, right? And we know that R has ATM. So we have to change our ATM, our torrs into ATMs. So how do we do that? Do you guys remember? How many torrs will equal 1 ATM? So if I remember correctly, I could be wrong. 1 ATM equals 760 torrs. And I believe you guys have that. There's a sheet.
Yeah.
Yep.
No, I don't know. But yeah, I just looked it up right now. 760.
Yep.
Yeah.
Yeah, I need to get you guys that. That's from Melissa Maribel. Okay. So then pi is going to equal. I have to give them the packet. Yeah, I have to print it out. Yeah. I have to see what I did with it. My computer is getting so cluttered. Okay. So that's my pi. Okay, so my pi is going to be 9.7 times 10 to the minus 4 ATM. We know our temperature. We have to change our temperature to Kelvin. So T equals 27 degrees C plus 273, which is equal to 300 Kelvin. And we know that R, put this R up here, is going to equal to 0.0821. And that's ATM. I'm struggling here. Come on. ATM liters. Moles. Kelvin. So if we solve for our M, and we know that M represents, well, equals our, well, not molarity. Yeah, it does represent molarity, right? Molarity. So then that's moles over liters, right? So I'm going to use N over V, if you don't mind, to make it a little, eraser. N for number of moles, N over V. And we're given our volume, right? What's that? Okay. Yeah, she's probably not expecting us to be here. Okay. Okay, so then I'm going to plug this into this equation. So we'll get pi equals N over V RT. And then we're going to solve for N. So N is going to equal pi V over RT. And then we can plug in our values. So we have that 9.7 times 10 to the minus fourth ATM times 1.00 liters divided by 0.0821. 821, and that's ATM liters over moles Kelvin times 300 at the bottom, Kelvin. Okay, so then we get N equals so we get 3.9 times 10 to the minus 5, and that's moles. So if we're going to calculate molar mass, then we would do what? Okay, so we divide 10 grams by our number of moles, which is 3.9 times 10 to the minus 5 moles. Molar mass. Okay, and what do you guys get? It should be a big number, yes. Good. It will be 2 sig figs, so our molar mass, sorry to write all over the place, it's going to equal 2.5 times 10 to the 5th. Yeah. And that's grams per mole. Yeah. Come on, where is it? Come on. Yeah, proteins they have very high molecular weights because you're adding a whole bunch of. Okay, questions, concerns, Cash, Kool-Aid? Okay, so let's add more knowledge, yes. Scott. My computer is not responding so today. We got two more slides, then we'll be done. Then, okay, so the colligated properties of electrolyte solutions. So in this case, we're going to add another factor. This is called the Van Hoff factor. Now, the Van Hoff factor basically says that, okay, these solutions are dissolving. So that means you got to take both of them in consideration, right? Because now you have two things that are going to be contributing. You have that plus charge and you have that minus charge, right? So you have this I, which is going to be a correction factor, okay? So the equations that we have now, right, for our boiling point elevation, we just add the I onto it. For the freezing point depression, we add the I to it. And for the osmotic pressure, we add the I to it, okay? Yeah, we're adding one more letter. So now this I is just going to be the number of ions that you have total, right? So for instance, if we have calcium fluoride, how many ions do we have? So what is the chemical formula for calcium fluoride? 3, that's right, because we have 1 calcium and 2 fluorides. So then our I factor is going to be a 3, okay? Okay? That's right. Yeah. Okay. So if we were talking about sodium chloride, our I factor is going to be sodium chloride 2. That's right. If we were talking about sugar, our I factor is going to be because it forms a covalent bond, so it's going to stay together. So it's going to be a 1. Does that make sense? Because it doesn't dissociate. That's right, because it doesn't dissociate. So no, it applies to stuff that dissociates, right? So the I applies to stuff that dissociates. That's right. that doesn't dissociate. Yeah. So like for instance, sugar, it stays together. It's a one molecule, so it's not going to dissociate. So it has a I factor of 1, right? Water would be the same way. It would have an I factor of 1. Yeah. So, but sodium bicarbonate would have an I factor of 2 because it's NaHCO3, where the HCO3 stays together. Okay? Okay, so calculate the freezing point for a solution of 0.72 grams of calcium chloride solution in 175 grams of a K with a KF of 1.86 degrees Celsius per molal. Okay, what did you guys get for the molecular weight for calcium chloride? Got 110, I got 111. Okay, so that's going to equal 0.00652 moles. And then we have to change water into kilograms. So then that's, yeah, so we divide this guy by 1,000. Grams equals 1 kilogram. So that's going to equal 0.175 kg. And I'm running out of room again. So then my M is going to be 0.652 moles divided by 0.175 kilograms. So I get my molality, molal equals 0.0373 moles per kg. So we know our I is going to be 3. Delta T is going to equal 3 times 1.86 degrees C over molal times 0.0373 molal. It's going to cancel out. And we're going to be left with Celsius. The change in temperature is going to be 6 times 3. So did you guys get 0.208 Celsius? So if our T initial, delta T, represents T final minus T initial, so our T initial is going to be 0, right? 0, or T initial minus T final. T is going to represent T initial minus T final. Ti minus T final, right? It doesn't matter, but well, it does, but it doesn't, because the answer should be a negative, because water freezes at 0 degrees. And so now we're able to go down to negative 200 N. I mean, negative 0.208. Does that make sense? So sorta, it sort of matters. Does it make sense? Yeah. because it's depression. So the new freezing point would be -2. If we solve for that, T freezing point, F is going to equal -0.208 degrees C. Okay, questions? Bless you. Okay, last slide for the goal. Last thing that we want to talk about, so we've talked about solutions. So we also have colloids and suspensions. Now, so solutions, we classify a solution as something that we have equal distribution of everything in, okay? So the difference between the three classifications is the dissolved solute is determined by particle size. So colloids or colloids dispersions consist of larger particles that are dissolved in the solvent. Okay. Colloids basically differ from solutions because the dissolved particles are not individual molecules, but rather they're aggregates. So kind of like, like tapioca, the pearls, yeah. Okay. So, and these aggregates may not easily be observed by the naked eye, but they can be. But they can also be observed by the scattering of light. Yep, Orbeez is another example. Yep. Okay, so immersions are often colloids. So like, have you guys made a meringue? A meringue, like for a meringue for a pie, or something like that. Nobody's ever made meringue. Or frosting. Have you made frosting? You made frosting. So that's an example of immersion. That's also an example of colloids, right? So even though that it looks like it's all evenly distributed, but they're kind of larger in size, those molecules that are aggregating together. So the sugar molecules and the butter and all that stuff. Okay. Milk is an example of colloid. Regular milk. Yeah. Okay. Let's see. So soaps is another example of a colloid. So, but those are like examples of ones that we can't, like we need light to sit there and distinguish between the different particles, right? Okay. So, so basically, soaps are basically used as a cleaning agents. And the way that they actually work is that they surround the dirt, right? And so that allows them to sit there and be picked up. So, a suspension is a heterologous mixture with aggregates that are larger than the colloid. So you're not getting that nice distribution, right? So kind of like if we take sand and water, right? That's a suspension. Okay. Questions? Concerns? Anybody want to give me money? Yes. You guys are missing my slides now. Yeah. Well, I'll take a piece of gum. You guys are definitely missing my slides at this point, right? These are kind of dry. I'll work on them. I'll try to make them spruce them up. You charge me. Huh? Exactly. I know. What's that?